Hello everyone, today I'm going to talk about why neural nets can approximate any continuous functions. So I've been thinking about this question for a very long time, and recently I came across a very good and very simple explanation which is in this link, so I wanted to share with you guys. Firstly, why is function approximation very important? Because a lot of tasks can be seen as function approximation. For example, in image classification, we're basically trying to find a function f which map the image to its corresponding class. And also for translation, we are basically trying to approximate the function f which basically map the sentence in one language to another language. Because the neural nets can approximate any function so well, that is one of the reasons why neural nets has been so successful in many different tasks. Okay, so let's do some simple analysis of how we actually want to approximate any continuous function. For example, if we have a blue curve like this, a very simple way, a very naive way to do that is to approximate this curve using a bunch of rectangle function. So we can see that this blue curve can be seen as a combination of a bunch of rectangles. And so if we have enough rectangles, then we can approximate this blue curve very well. Okay, so let's see how we actually want to approximate using these kind of rectangle functions. So as a simple example, here we use 3 rectangles to approximate this kind of this blue curve. So if we do the further decomposition, this one can be seen as the summation of these 3 rectangle function, the yellow one, red one, and green one. Okay, so the question becomes, how do we want to approximate the rectangle function using neural nets? If we are able to approximate these kind of single rectangle functions, we are able to very easily approximate its combination. Okay, so how do we want to approximate this kind of single rectangle function? So here we should notice that a single rectangle function can be further decomposed as 2 step functions. So one is stepping upward, the other one is stepping downwards. If we add up these 2 functions, we can get the original rectangle function. So now the question is, how do we want to approximate these step functions? Okay, let's go back to one of the important components of neural nets, which is sigmoid function, which is often used as a activation function. So in sigmoid function, we usually have like 2 hyperparameters, 2 parameters w and x0. So the function form is like this. So we want to see how we can adjust these 2 parameters to actually change the shape of the curve to make sure it can approximate the step function. So here I show an example of the of our sigmoid function. So first, if we adjust the x0, we can see that it's basically shifting this curve along x-axis. So it's basically making sure that the center of the curve is at the x0 position. And if we adjust the w, we can see that it basically changed the steepness of the function. So it goes from very smooth, not steep curve to a very steep curve as we increase its w values. Okay, so if we notice this, then we can easily see how we want to approximate this kind of step function. What we want to do is just to make sure that x0 is set to be the position of step. So if the step happens here, we set x0 to be here. Okay, and to get the sharp, steep step function, we want to make sure that our w is very large. So in this case, we want to set w to be a very large value. So if we set these 2 parameters, we can easily approximate a step function using the sigmoid function. All right, so let's see what we have right now. So we are able to approximate these step functions using the sigmoid function, and also we can combine the step function to get this rectangle function. And we are able to combine a bunch of rectangle functions to get a series of rectangle functions which can be used to approximate our original curve. Okay, so mathematically it's basically written as this. The original curve can be seen as the summation of the linear combination of the step function, which can be seen as the approximate as the sigmoid function. So it can be written as this, which is the linear combination of a bunch of sigmoid function with different kind of parameters wi and xi0. So if we see this, we can basically see that this is exactly the neural nets with one hidden layer. So basically this leads us to the universal approximation theorem. It says that a neural net with just one hidden layer, if enough neurons and uses a nonlinear activation function, can approximate any continuous function. So okay, so that's for one-dimensional case. So how about multidimensional function? So in the link I show at the very beginning, so this link, they basically provide a similar idea for constructing rectangle function in high dimensional space, so that we can use these kind of high dimensional rectangles to approximate any continuous functions. Okay, so that's all we want to talk about. Thank you for watching. See you next time.